Hi, I'm Cris Barnes from Sandia National Labs, and I'm here to introduce Cris Barnes. He's the program director and marine capture manager at Los Alamos National Laboratory. He's been a staff member at LANL since 1981, and he's served a variety of positions in Washington, including working for the Office of Defense Science at NNSA headquarters. And from 2013 to 2014, he served as the Los Alamos member of the NNSA Defense Program Science Council.
So thank you, Bill, for the story about the history of the Mossbauer effect. It reminds me of a couple of lessons I've learned in my life. No one is more critical of their own data than a good experimentalist. But there are times, which I hope you all get to have, when you have an epiphany, when you look at your data that you've been highly critical of, and you suddenly realize, no, this data is actually right. The theory is wrong. I've really learned something. I've had the good fortune to have that happen in my career a couple of times. I want to thank the SSGF for inviting me to give this talk to this wonderful audience. I'm going to talk to you about the matter radiation interactions in extreme project eventually. First, I want to tell you about mesoscale science and the challenge. And it's people like you that I'm doing this for. It's people like you who want a future of great science in this country that I am spending my life now at this time trying to build a $2 to $3 billion project. I do have to say that it's very intimidating having a business session next door in which they're able to make the audience laugh or clap every minute or so. So if I do say something even slightly funny, or if something that you like, by all means, break out into applause, okay? It'll make me feel much better compared to them. Thank you. Thank you. So you are National Nuclear Security Administration graduate fellows or alumni, and NNSA gets a lot of money, $8 billion a year and growing, to build stuff. This is, although it's got LANL logo on it, this isn't sort of an official NNSA slide. Bill Rhodes will know it well. And it describes the current strategic plan of NNSA to take our old stockpile of a whole bunch of weapons, very bad laser pointer. If somebody from Livermore has a better one, by all means, I'll take it, and turn it into a lesser number of them and try and modernize a stockpile that was built during the Cold War, has gotten very old now, and needs to be refurbished in order to maintain the nuclear deterrence of the United States. Bottom line is that NNSA needs to make a lot of stuff in the next decade. They need to build a lot of things out of materials. Now you're going to hear me pitching this talk a lot about the mission need for NNSA and defense programs, because quite frankly, they're the people through Congress who are going to hopefully give us a bunch of money to build an experimental facility. But you can immediately realize that people around the world make a lot of stuff for a lot of things, whether it's cars or new manufacturing equipment to build other sorts of things. The issue of making new materials, materials that can last a long time, materials that you need to have confidence throughout the life cycle, is an overarching theme for our country. But NNSA has a real need because of the critical nature of the thing that we do. This is a view graph that comes from the words of a fellow by the name of Bob Webster, who just got promoted yesterday, literally, to the second most important job at Los Alamos, the Principal Associate Director for the Nuclear Weapons Program. You are stewardship science graduate fellows and alumni. Stewardship was a term coined in the 90s when we stopped, thankfully, doing nuclear testing, but realized we needed to maintain a nuclear deterrent. And the problem at that time was basically making sure that we could still be certain that when the President of the United States said, push the button, make it go boom, it would work. And for that matter, if he didn't tell you to do that, it wouldn't go boom under bad circumstances. There's both those, it's the always never clause, which makes our job so hard. And we've learned very well how to do that. We've gotten better and better at predictive capability, at understanding how the weapons that we have actually will behave even when you can't test them. This is a really hard problem. Imagine somebody who has to design an F-35 for use in time of war, but you're never allowed to fly it at supersonic speeds. But when war comes, you have to know that you can take it to supersonic speeds and it will work. That's a very difficult problem. And you're going to build that F-35, put it out there in the field, and essentially expect it to last for 30 years. So this is a hard problem, and you're building it out of materials. But in the future, we're realizing that there's a broadened emphasis. We have to start working about the entire life cycle of the weapons. More and more of the issues that we face have to do with production issues, have to do with surveillance issues, have to do with things that happen during the entire life cycle. And most of those problems are coming up in materials. And the cost, one reason we're getting more and more money, is this is a very vital national need, and it's costing more and more money to keep dealing with these old weapons the old way. We've got to change to something new. So Don Cook is the Deputy Administrator of Defense Programs. He is retiring, he is about to go, so he is a lame duck, but right now he's still the boss. And he has said his #1 priority is Exascale and additive manufacturing and MARIE, an experimental facility for measuring materials that you're making. And the reason he says that is he realizes we've got to change the way we make things. We've got to use big fancy computers to be able to understand how they're going to behave throughout the life cycle. He thinks that additive manufacturing is an example of a technique where we can make things faster and maybe better and therefore maybe cheaper in order to do it, but you won't believe that you can use additive manufacturing unless you have the science to go with it. And it's all three of those together which will give our country the science tools needed to do that. And so Exascale is being funded. It's a big program and growing in the United States right now. Additive manufacturing initiatives are growing, and applications are being found and used. I'm almost embarrassed to say I'm this old, and I have a Twitter account, and I use that for reasons I'm not quite sure, maybe to communicate people, and I try to search out things on Twitter about Exascale and additive manufacturing and passing them on, mostly to educate myself, to try and learn about these new techniques of what people are doing in advanced manufacturing and where the problems are in certifying them and so on. And so the MARIE project is actually trying to get a critical decision zero, it's called in federal bureaucracy, a decision that there's a mission need for a science tool to understand the science behind making these new materials. It's not just about making parts, it's about making materials and having confidence they will work for the entire life cycle of the device. That is the great challenge. Now again, it's not just a challenge involving nuclear weapons. These scientific challenges have been workshopped nationally throughout the whole field of material science. You can't read these, but in particular, I encourage people who find my talk in the slightest bit interesting to find this Opportunities for Mesoscale Science report out of the Basic Energy Sciences Advisory Committee in 2012. And it will lay out very clearly the basic science issue about materials at a scale between the atomic scale, where it's about the periodic structure of the materials, and the continuum scale, the scale of a full-size device. And there's a gap in the middle between that atomic and continuum scale where we have not in the past had as many tools and abilities to look at, and where the science opportunities are the greatest. And you can read about that there. There's the Materials Genome Initiative, in which people are trying to figure out how you can better discover new materials. There's advanced manufacturing initiatives. Everybody is basically looking at everybody who is my age and doesn't do real science anymore, as the young people are oftentimes telling me, are looking for what the future frontiers of the business are. And the future frontiers are in this middle or mesoscale. And that's a scale of basically microns of the material and nanoseconds for sound waves to cross over that region, plus or minus a couple of orders of magnitude. It's a region where the dominant effect on how the material behaves is not due to its periodic structure, but is due to its defects, interfaces, the voids that are created, say, by radiation damage, its random, stochastic, intermittent issues in there. One of my favorite quotes is from my colleague Dan Toma, just left Los Alamos to become the director of the Granger Institute of Engineering at the University of Wisconsin. And He, who has been a world-class metallurgist for years, says, materials are like people. It's the flaws that make them interesting. And it's the flaws in this middle scale that we want to go after. So I mentioned exascale, additive manufacturing, and Marie. So again, the way science works is that smart people get together and they do a workshop and they try and find commonality and challenges and big questions and write it up in a report and then use that to convince people like Bill Rhodes that that's where they ought to be putting their money forward. And so there's been a lot of work on exascale computing. And the big initiative in the Department of Energy is a joint project between the Advanced Strategic Computing Initiative of NNSA and the Office of Scientific and Computing Research in DOE, with lots of other people playing in this, because NNSA, as many of you may know, has, since the era of stewardship began, been the leading driver of high-performance computing in the United States. We aren't always the best, but we're always striving to be the best and pushing forward what the best may be. And as people think about what you would do with an exaflop computer, the problem is that you can end up with such a computer and it can do a calculation really, really fast. But if it's calculating the wrong thing, if it's got the wrong models, it's not going to give you any useful answers. You need to know what the mechanisms are that you want to model. You need experiments to discover those mechanisms. Once you've found the right mechanisms in your modeling, you need to make sure that your numerical methods actually are valid for solving those in the domain of interest. You need to have an experiment that can validate that the code is right. And in general, even with exascale computers, you can't do everything ab initio first principles. You need to make approximations, reduced order models, and so you need to calibrate what is going in to those models. And so experiments are needed to discover, validate, and calibrate the exascale codes. I find it interesting when I read strategic reports by the people who are pushing the exascale initiative. All those computer scientists can just talk about building big computers. They're fine. When I talk about trying to develop the mission need for an experimental facility, I'm tied in very closely to what the computers are doing. I talk a lot about what the exascale computing are needing because I know that they work together. In particular, if you think about what going from a petaflop to an exaflop gives you, okay, that's a factor of 1,000 in speed. Sounds like a lot. But unfortunately, if you're doing a 3D problem, that's only a factor of 10 in resolution because you also lose a Courant condition on your time. And so you actually don't even get a factor of 10 out of a 1,000-fold increase. You do get somewhat higher resolution. You can get higher fidelity, but you generally have to just use those extra computational cycles to get smarter. One approach has been called adaptive physics modeling, where say you want to model a shock moving through a continuum, and what's interesting is what's probably happening at the shock front. And so your calculation may be coarsely zoned out here and over here, but as you get closer and closer to the region where the physics is changing rapidly, your code may zone it up more and at some point may spawn off things like MD simulations to give you an instantaneous equation of state for just exactly what the material's condition is at that point. Or it might do some sort of a single crystal model of how the orientation of the crystals are going to matter to the shock front in that zone, issues like that. That is how exascale can be used. The question is, will we have experimental capabilities to be able to address that? So that's exascale. How about additive manufacturing? So I'm originally a plasma physicist, and I've been slowly learning material scientist as I've basically gotten fascinated by this field and what the challenges are. And so I didn't learn about the materials tetrahedron in graduate school, as, for example, Cris probably will at Georgia Institute over there. But material scientists have learned that what determines the performance of a material isn't just the atomic structure. When you take a piece of material and you bend it till it breaks, it's the force you need to put on it is not given by the atomic bond strength. It would be really hard to break things if they only broke when you broke the atomic bonds. What you tend to do is you find the occasional voids, fractures, grain boundaries, and so on, and those are what open up, and those are what make it fail, and they tend to fail 10 to 100 times more easily than the atomic structure would tell you. It depends upon what the actual structure of the material is, and that structure can depend on the processing of it. We all like to make fun of each other's fields and so on. So again, as a plasma physicist, I love the term heat and beat, because that's what material scientists do, is they heat the material up and then they beat it. They roll it out and then they heat it some more to anneal it, and then they pound on it some more and then they heat it. People making swords have been doing this for thousands of years. Metallurgists have gotten really, really good at being able to do, macroscopic things with metal, going through this heat and beat process, and a lot of it is magic. I don't know if you're a Game of Thrones fan, but there's Valyrian steel that people have, and so there's some, if at some point you can heat it with dragon fire, it gets even better. Marie is going to try and figure out what does dragon fire do to Valyrian steel so that you can reproduce it in the manufacturing plant. That's sort of the kind of concept, because there's something going on about how you add things. I didn't catch your name, but you're working on nanomaterials and so on, 2D materials. And he wants to do what's called controlled functionality. That's the fancy term that we use in our material strategy at Los Alamos, is how do you achieve controlled functionality out of a material? How do you take a material which is strong, but then give it also electromagnetic properties of a certain sort? Can you predict how you would do that and then make a process that would put that together and end up with such a material? I really love the book, How Google Works. Well, I also hate it because I wish I worked there. I was 40 years younger and could work there. But it's a cool place. And one of the great things that the Google people have taught us is to not worry about, say, oh, you can't do that, but say, what if you could do that? What if you could figure out a recipe of how to mix the materials, how to process the materials, how to structure them in a 3D printing type way, such the combination of that atomic structure, that processing, the properties you put in from the special impurities, all combine to give you some controlled functionality, which you then knew how it would last for 30 years. If you could do that, that would be great. All right, so how do we get there? And our answer is, you need to be able to see the material while you're making it. So, some examples of things, we do a lot of shock physics in NNSA experiments. We take a chunk of material and we throw a flyer at it or shoot a laser on it and put a stress wave across it, and we then basically watch it. People have been doing this for many tens for decades, many tens of years, but they tend to look at the surface of it and look at surface waves, and they decode from the surface waves what's happening deep inside. And clearly you'd be much better off if you could radiograph in the middle. I don't think anybody can see this in the room, but there is in these proton radiographs, the shock waves basically traveling inside of the material, and you can measure the width of them and tell something about the kinetics and so on. What you'd like to be able to do is look at the actual individual grains in there and how they're phase transforming in time and make movies of what's going on. And if you could actually do all that, let's not worry about how you would, if you could do that, suddenly you start uncovering a whole new layer of understanding about what's going on in the world. Another lesson I've learned as an experimentalist, when you come into a new field, half of everything that you're taught about that field actually really isn't as well justified as the people telling you say it is. And a careful reading of the literature, you may find out that, well, why do people think that? That was kind of a crappy experiment, and they made sort of these odd assumptions. And if you go and you look at that, half of those things, half of them will turn out to be true, but a half of those things that aren't well justified aren't true. And so there's an awful lot of opportunity to really re-look at the assumptions of the business. Again, forgive me for picking on Cris, but we were just at the same conference a couple of weeks ago in Tampa, the Shock Compression and Condensed Matter meeting. And as I'm sitting there and I'm listening to people, I'm seeing a sea change in thinking. That there's so many people at that meeting who were trained by the demigods of the business, who believe in the Rankine-Hugoniot conditions and assumptions of steady state this and so on and so forth. And it's not true. That's not really what materials are. The biggest lesson as a plasma physicist I've learned about material science is that equations of state aren't. They are not equilibrium. You tell me the pressure and the temperature and I tell you the density. Load dependent, time dependent. They are not equate. They're really good approximations for doing certain types of calculations. And so this is the challenge that you have, is to come in and start saying, okay, what if I could get at time-dependent information and movies and the details like this? What could I learn and understand from that? We work a lot in energetic materials in NNSA and for our colleagues in the Department of Defense. One of the biggest issues is what actually initiates a detonation. So right now there is a hypothesis out there, and it's really funny in our business that scientists will basically come up with some hypothesis, and at some point enough people think that that's a good hypothesis that people start acting as though it's true. And the idea is that real materials, I guess I don't have a picture of real HE, but it's basically single crystals of energetic material with plastic binder in between, and it looks like just, a random mosaic mess. And there's all these cracks and gaps, and people say, as the shock comes through, you have these gap regions, and they squeeze together, and the voids heat up and make a hot spot. And that makes the chemistry run away in an Arrhenius way of doing things, and that starts the chemical reactions off. Well, if there's one thing that we've learned about the National Ignition Facility is that maybe implosions aren't quite as good as you think they are at imploding and heating things up. Maybe it's not hotspot formation that's going on, but we can't tell. It's a scale that we don't currently have tools that are fast enough or able to image these random things well enough to be able to see what's going on. Now, I'm going to tell you about an experimental facility, eventually, like in the last couple of minutes of this talk, which will be able to do it, but it's a long ways in the future. One of the other lessons to take away from this meeting is, Marie may never get built. It's a long ways away, but wow, aren't there a lot of great opportunities now? I can think of a way to do that experiment now on a present facility, and not as well, but still well enough to actually get at the science, because I don't believe it's hotspots. Or maybe if I go and I do it this way, I can determine it is a hotspot. It's like Mossbauer essentially suddenly having this epiphany that, if I go and I do this little Doppler shift thing, I'll really see the effect. Now I can see that I can do that. So I talked about this middle scale being all about random defects, interfaces, voids, random things. It's not so much about the periodicity of the atomic structure, which is still very important and needs to be maintained, but it's about more random stochastic effects of the materials. And imaging is really important. And you are living right now in a revolution in imaging science. There's a really nice review article in Science magazine from early May by John Mao and Ian Robinson and Margaret Muname, and I don't know Ishikawa-san, but this is one of the pictures from it about how people are able to use coherent light to get at resolutions of imaging like no one's been able to do before. And that's an important idea that we have tied on to for Marie, that there's a revolution in coherent imaging, and so we want to build a coherent light source. So X-ray imaging techniques can give you sub-micron resolution. They can get at this mesoscale, and you can do it with optics. There's actually a lot of really fun stuff going on in optics right now. These kiniform lenses everything I thought I knew about X-ray optics got blown away when I finally understood how these things really worked. But you can take a plane wave of light, you pass it through an object, and you can look at the absorption, the change in the real part of the amplitude of the field. You can look at it in the near field and in the far Fraunhofer field, and there's various techniques that have various strengths and weaknesses of doing that. So there are different people who use these various techniques of using X-rays, and they can use optics or not to try and give them resolution. So let me go through a quick refresher perhaps on what it means to scatter light. So if you have, if you have an incident electric field impinging on a sample, the electron density in that sample will basically scatter the light. And the light will move off to some distance here, and there will be a perturbed, scattered electric field someplace further down. And maybe you have a detector there where you want to detect it. So one can work through the Helmholtz integral math of this scattering And in the limit where, so let's go back to my definition. So let's call A the size of the beam spot, the size of the region that you're illuminating. And let's, lambda is the wavelength of the light, and you're going to look some distance z downstream. So with those definitions, you can then basically work out that if this Fresnel number, which is the ratio of the beam size to the wavelength and the beam size to the distance, is very much less than 1, a very complicated complex integral reduces to this form, and even an experimentalist can recognize, oh, that's the Fourier transform of the density. And so I'm basically saying that in the far field, when z is big enough to make this number very small, scattering is like a Fourier transform. And suddenly all sorts of wonderful techniques open to us. And so this is a famous picture from a paper in the, gosh, I guess it was only about 10 years or so ago. Or maybe, yeah, this one I think was from Flash at LCLS about 10 years ago. So they had some lithographed little object. This is the scattering pattern of it. And then they did, in a way I'm going to discuss, a reconstruction of that to basically say what the image actually looked like. So this is now one of the biggest businesses in the world of science. You may hear a lot about the Large Hadron Collider. It's got nothing on LCLS. And when the European X-ray free electron laser comes up, there's just amazing stuff that people are now doing with this. I predict that Henry Chapman and people will win the Nobel Prize in the next couple of years for doing the single crystal imaging of biological materials and making movies of them at LCLS. And so this is an incredibly powerful technique. Now, one problem that we have on Marie for the mesoscale, let me go back to this formula here. Again, our problem is we're trying to look at a large region. So A is going to get big, and A squared is going to get really big, because we want to look over a mesoscale region, a scale much bigger than the optical wavelengths. And so unless you move a long ways away, a kilometer away for your detector, you can't get the Fresnel number less than 1. Now, when I started thinking about this about 7 years ago, I was told that diffraction only worked in the Fraunhofer regime, in the far field. I was told that. Fortunately, I'm an old man, and I've been told many things in my life, and I don't believe them usually, so I basically looked into it. I'm also an old man, and I've learned something, and that is I find some young kid to work with who's smarter than I am, and John Barber worked out the math in which basically if you, there's a number which we call the small angle number, and if that number is small, and you can make that number small by just having your detector and your distance basically set up, the Fresnel integral turns into something that looks like this. And in this case, it basically becomes a Fourier transform of the electron density with a phase factor on it, which is easily computed out. So you can still get a Fourier transform in the near field. You can do this for arbitrary Fresnel numbers. And that suddenly makes mesoscale imaging, using coherent imaging, workable. And so that was a really fun breakthrough. Okay, so let's talk about the fact that those integrals are complex integrals, yet your detectors don't measure the complex field. Now again, forgive me, there are already people thinking about how you can maybe get 2 detectors, and by measuring with 2 detectors, work out the phase as well. So I'm a firm believer in Arthur Clarke's first law. If an old scientist tells you something can't be done, ignore them. If an old scientist tells you something can be done, listen to them. So I think there's some really cool things you can do with the math. But if all you're able to measure is the real part, the absolute value of the Fourier transform, you can still do phase retrieval. Okay, so let me explain iterative phase retrieval a little bit. So I hope this, some of you, I think you, for example, probably know this extremely well. Many of you don't. This was a real epiphany for me for the last few years, so it's a pretty cool technique. So again, we start with some sample, something that you want to image, and we scatter off of it, and we get a intensity form onto a detector downstream. And that, of course, doesn't look anything at all like that. And what we've measured is we've measured the real part, the norm of the absolute value of the complex field downstream. Okay, so we basically take that field of amplitudes and we randomly assign a complex phase to every pixel in it. Just completely random. And we then go and Fourier transform that, and we basically get a prediction of what the object was that we scattered off of. That prediction doesn't look at all like the real object. But now you can enforce what is known as support. If you've oversampled over here more pixels than you actually have in inverse space from the original detector, you will have predicted that there's some amplitude out where you weren't illuminating or out where there wasn't actually any material. So you can go and enforce those constraints, such as setting the density to be 0 where you know that it has to be 0, and then re-Fourier transform that back into Fourier space, and that will now make a prediction of both amplitudes and phases from that object. You replace the amplitudes with what you measured, but you keep the phases that you calculated here, and you go around again, and you go around again and around and again and around and again, and it converges. It's been proven that except for mathematically weird circumstances, it will always converge, I've been told. I'm not a good enough mathematician to understand the theorem, but it does actually converge. So let me give you an example. So here is the first trial prediction of what an object looks like. We've taken the object, we've scattered off of it, created a Fourier transform, we've then thrown away the phases, and now we're doing iterative phase retrieval on the Fourier thing. And so this is the first prediction, and I don't think anybody can say what it is. So let me go through that more slowly here. I'm not used to this computer. So iteration by iteration, you basically continue to apply constraints on what the outside is doing until it finally converges. That's the famous face on Mars image, if anybody has seen that. The process can give you imaging even though you can't measure the phases directly because you get extra information from some other place. It can be from support over the size of it, it can be from other diagnostics. Actually, this is going to be a really big field in future years, Bayesian inference and using multiple detectors in order to try and provide support for various things, but you can get actual imaging out of a coherent light beam without need for lenses. So here are some examples at large, very much greater than 1, Fresnel numbers. So if the Fresnel number is 0, classic iterative phase retrieval in the Fraunhofer regime, here's a scattering pattern, and after 500 iterations, you basically predict what the image looks like. But you do it at 20, the scattering pattern again looks kind of similar but different, and you go through the iterations, it actually converges faster. We do not have a mathematical proof about why it converges faster at larger Fresnel number, but it actually, the iterations seem more robust. At 200, which is really getting to be in the near field, it sort of starts looking like a phase contrast image in some sense. And actually there is a relationship between coherent X-ray diffractive imaging and phase contrast imaging. And after just a few iterations, again, you can reconstruct what the object is. So you can use these techniques to make images of objects, and you can do it at the mesoscale with X-rays without it having to be in the far field. This then opens up a world of using light sources to look at materials. So we care a lot about polycrystalline metals in NNSA. So do a lot of other people, but in particular we do care about. So if you have a polycrystal, and unfortunately at this stage, most of my examples, theoretical examples in which we create an object, we scatter off of it, we see what the diagnostic signals, the theoretical models tend to be molecular dynamics models because that's what we're good at creating these sort of structures, and they're on arbitrarily wrong scales and so on. But again, you can take an MD polycrystal, you can create the diffraction pattern, and you end up getting an image reconstruction, which is essentially in 2D a projection of what the 3D object looked like. And so this is actually a slice through it mathematically. This is actually more of what this object would look like if you scattered a beam off and then tried to reconstruct it. Now, right now, the problem at LCLS is that you take an object like this, say a nanocrystalline piece of material, you scatter off of it, you get your image, but the laser intensity was so high that it turned it into a plasma, and it's gone. And you don't know how that defect interface over time evolves, because you weren't able to make a movie of it. What if you could make a movie? So here's another example of what you can do other than imaging. Scattering is still important. So this is a classic experiment that we do a lot of, in which you essentially have a flyer plate that impacts on some sample, this way, and a shock wave is going to travel from one side to the other. The X-rays are going to come in from this direction, scatter off onto your detector, and you're basically looking at the X-ray diffraction pattern off of such a interaction. So watch in the blue, I'm just going to kind of push through it fast. You see some spots coming and going in time. So if you look on the left, you'll see a shock wave going through and a refraction wave catching up. Shock wave bounces off the top and they meet. And so at some point, as you go through this simulation, spots appear and disappear in the diffraction pattern of the image and tell you what must be happening to the crystals in that particular region there. So this is pretty complicated, but clearly you can see that you can be scattering off of the crystals. If at the same time you can be imaging what the crystals are doing, you can start getting a pretty detailed look about what's going on. Actually, it's intimidating just how detailed it is. And it starts raising another really important challenge that's already hitting people today. The dirty secret that we have in a lot of what we do in NNSA science is we collect too much data. Now, don't listen to this, Bill. No, don't cut science campaign funding, please, okay? But we have so many great emerging tools, whether it's NIF or Z or Omega or LCLS or DCS at APS, that people are going and taking really, really great pictures of data and so on, and they do really gee whiz, wonderful view graph that makes people really excited and want to give them more money, and it's really hard to analyze because we're starting to get so much information out of some of these experiments. And the theorists and the computational people aren't quite yet keeping up. Because what you need to do is you need to be able to make the sample, characterize the sample fully, run a whole bunch of calculations on that sample using different materials models to predict what the difference is going to be in the performance of those crystals, make a prediction of what your diagnostic signals are going to look like based on those different models, tell the experimentalists where to put the detectors to see the maximum effect, you know, going from a 1 in 10 to the 5 type of effect to a 1 in 10 to the 2 type of effect, and then do the experiment and analyze it and use it to validate and calibrate the data. We call this the broader concept of co-design, of a tight connection between the theory and the computation and the materials making and modeling and the measuring back to then impacting on what the calculations are doing and the models and so on, and doing that rapidly to advance the science. And it's when you've got this much type of data, when you're trying to uncover something like this, it's really tricky. But again, I'm talking about trying to make movies. Right now, I see a colleague back there, Rick Krause, and he's part of the team on NIF who do a lot of diffraction experiments on NIF. And they tend to take a material that kind of looks like this, and they run a shock through it, kind of like this, and at one instant of time, bang, they hit it with an X-ray pulse, and they diffract off of it. And they get one of these diffraction patterns, and they learn a whole bunch from that, a whole bunch. What we'd like to do, what you would say if you were a Google employee, is what if you could do that continuously throughout the entire evolution of that material? What if you could make a movie of that? Okay, so how do you even begin to think about making a movie? So we're talking about trying to build a light source, and the key performance parameter energy for it is about 42 keV. And that 42 keV energy light source is a trade-off between difficulty. I'd like to be at 60 or 70 keV, but that's technically more risky and more difficult. And what you want to do is, so this is cross-section for X-ray interactions with matter. And these curves are for different materials: uranium, iron, and aluminum. So aluminum's the lowest one, iron's there, uranium has the higher cross-section. This is the total cross-section, including all the absorption, all the things that basically suck up the X-rays, turn it into a heat, and turn it into a plasma. If you're living down here at 8 keV, all these materials suck up a whole bunch of X-rays in one blast, and poof, they turn into a plasma. And so you want to be as far out this way as you can to be lowering the temperature. And this is decadal, orders of magnitude less absorption out here. This is the elastic cross-section, the cross-section for the good signal, for what will tell you about the scattering. And it does drop with energy, but not as fast. And you can see that the ratio basically is peaking in this many tens of keV range. And we believe that you can basically get to a situation out in the high tens of keVs where for thicker 100 micron type samples, you can scatter as many as about 1% of the photons will give you good signal. You still have to live with that other 99% of the X-rays that come in and heat your sample up, but you're spreading them out over a bigger region to do mesoscale sampling. And if you work your way out of the box, experimentalists have this term for basically, what's the experimental box I'm in? You have these walls of, I can't go higher than this in energy, I can't go faster than this in time. What can I do to live within the box to maximize my experiments? But if you define the box so that you can actually get away with not thousands of X-ray pulses without heating it up, but maybe tens of pulses. You could maybe make 30 frames of a movie of a mesoscale polycrystalline material during a shock event. You could continuously watch the laying down of 3D printed material over time without melting it, but with this incredible resolution of structure from scattering, from microstructure, from imaging. And if you combine it simultaneously with another really cool idea, which is don't just build a light source, add to it as many other types of probes as you can simultaneously to give you as much information, you can end up with a revolution in how we address material science. So we propose to basically make an X-ray source, a coherent source, because you need the coherency for the imaging, a brilliant and high rep rate source, so you can capture frames of materials very fast and a whole bunch of frames of this high enough energy to be able to see into and through the mesoscale without overheating it. And the 42 keV specific number which is out there is because it's aimed toward plutonium, which is the hardest material. Everything else, lower Z, becomes easier. To do that, you want an X-ray free electron laser. And the lowest risk, best way to be able to do that is building an accelerator, building a LINAC. Happen to come from a laboratory that's really good at accelerators. I'm not really good at accelerators, but I got plenty of friends who are. And so we want to basically build a 12 GeV electron LINAC to drive an X-ray free electron laser with a fundamental energy of up to 42 keV. And that X-ray, that accelerator basically would allow you to have macro pulses with variable, you say for this experiment, I want a bunch of pulses for a while and then a whole bunch at some particular time. And you can put in what you want for your pulse structure and make a relatively flexible facility. That's the general concept. I'm in this funny situation that you don't care about right now, but we've done a lot of pre-conceptual reference designing, and I could go on for a long time about the details of exactly what Marie could look like. But on the other hand, I'm dealing with the federal people who are merely determining mission need for a mesoscale experimental facility of some general abilities, and so we don't pick the actual place. So hopefully my Livermore colleagues will join me on an establishment of mission need, and then they can work with their colleagues, say at Pantex, and plan on building this at Pantex, those two laboratories. I mean, that's still a possibility. But the idea is that NNSA needs this science tool, and I hope you can see that for the many reasons that I've been talking about. So the matter radiation interactions and extremes experiment is the experimental facility for the time-dependent control of dynamic materials performance. Dynamic materials performance means the time-dependent changing of the materials while it's actually performing, but we also want a facility that can watch while we make stuff. I thought I had 45 minutes and I'm doing okay, right? Got about a couple more minutes? Okay. And so there's a mission need to build stuff for a stockpile. The challenge is at the mesoscale. To fill that gap, you need coherent, brilliant, high energy, rep-rated X-rays. So you do that with a multi-probe experimental facility and combine it all with theory and modeling and synthesis capabilities to give you the revolutionary facility that can actually control the materials that we make. I'm going to skip over that. So a pre-conceptual reference design of what it might look at Los Alamos. We currently have a proton linac sitting on a mesa. There is a canyon edge very close to here, but we're doing a geotech survey to confirm that this is still like 50 feet away from the canyon edge and you can handle that. And we build a accelerator along here, undulators in here, and then experimental halls basically down here in a lab and office building, and that would be essentially the facility that we would want to build in order to get at this future. So we have formally recommended to defense programs that they propose critical decision 0 to the DOE bureaucracy. That has gone very well. While we don't have all of the defense program signatures yet, they are actively working their way through. We passed an independent cost review of the DOE Office of Acquisition and Project Management just a couple of weeks ago. We're working toward a program management risk committee, all this stuff that you don't care about, but you care about that I do it well so that this facility gets built in time for your careers. And so we are hoping to get a signature on CD0 near the end of the summer and can start the project with money coming in FY17. And this will start driving a change in the field of material science as more and more people are going, wow, you could really do that. But I can do this now, and I can do this now. Many of you out here work in high energy density physics. You may not all work on NIF, but you work in that field. And I was at a meeting on NIF diagnostics in 1994, which is in time about now for Marie. And NIF didn't really exist, and the field of HED didn't exist, wasn't called that. But I watched that field over the next 2 decades as it went from, sort of whatever and grew into a big field doing lots and lots of stuff. So even before NIF got built, the HED community grew and grew. It was a great opportunity. I believe even before Marie gets built, there's going to be a tremendous opportunity for looking at these frontier issues of the mesoscale, of additive manufacturing, of combining theory and experiment in this co-design technique to learn how to get controlled functionality. Many of these issues have said these are going to be the big issues of the next decade and so on that you can get really excited about. And to that line, we, Los Alamos, but also Livermore and Sandia, they don't brand their work as the roadmap to Marie, but it is the same thing. We are doing science and technology on the roadmap to Marie today. We've identified that there are facilities like LCLS and LCLS2, like XFEL, like the dynamic compression sector at the Advanced Photon Source that we need to be working on today and doing the best science that we can and delivering to the program today to get support for Marie, but also because it's the right type of work to be doing. And of course, I can't resist showing this slide of, I call this the shiny happy people slide after the REM song. So these are some of the many people, maybe a little bit older than some of you, but not too much, who are staff at Los Alamos, working actively in stewardship science in its various guises and so on, who are involved in this. This is the sort of program which can reinvigorate a lab, an enterprise, and that is really why I'm doing this, is that I am trying to create a future for our labs, which I think are vitally important for our nation. And so with that, I will conclude and basically hope you see this possibility of Marie being this wonderful experimental facility of your future. I thank you very much for your attention.